clouds in the atmosphere. Satellites see clouds differently than human observers, and NASA scientists could never be in all the places they would like to be to collect data from the ground, which is why we need your help making observations.
So we've been traveling around the world using drones and this technique to map corals in 3D. And the biggest challenge we have with all of this data is how to classify it. How do we get the basic number of how many corals there are, how they're doing as a function of changing ocean temperatures? And that's where NemoNet comes in. So we built a video game that ties into our supercomputer, and you can download it and play it on your iPhone or iPad device. And what you're doing in that game is looking at our data sets that we are getting from around the world with these drones and helping learn about corals at the same time as coloring them and feeding data into our supercomputer.
On Planet Hunters TESS, we use data obtained by NASA's Transiting Exoplanet Survey Satellite, or TESS. So TESS is a space-based satellite that monitors the brightness of thousands of stars, and we need your help to find the planets within these data. In particular, we want to find the planets that the machine and computer algorithms tend to miss.
So auroras affect our technologies on Earth and in the sky, in satellites, and they move really quickly, and it's important to get an understanding of what they're doing, and citizen scientists can really help with that.
What kind of discoveries have citizen scientists made with this project?
So one big one is something called Steve, which is actually an aurora that can be seen further away from the poles than the usual aurora. It's very unusual. It kind of looks like an airplane condensation trail, but with a photograph you can pick up these amazing colors as well. By studying it further with satellite data and other data from the ground, we've discovered it's really like a flow-driven aurora. It's an east to west flow that is lighting up the sky and doing some amazing kind of new, unusual auroral activity that's still being studied now.
We astronomers thought that disks stopped forming planets after about 5 million years, but then the citizen scientists at Disk Detective started finding objects that were able to form planets about 9 or 10 times the age of that, so into the 40 and 50 million year old age range. And the astronomy community is still trying to figure out what that means, so it's pretty exciting.
The second is, once you have all that data, it really doesn't mean anything unless you have humans come in and help annotate what it is we're looking at. To put it bluntly, they're changing the world. I mean, we have mapped, as of 2020, around 6% of the ocean floor.
Project in 2006, I think we had like 5 teams participating. Now we've got over 3,000 teams from 80 countries around the world that participate. Citizen scientists are able to look at these images and see deeper into the images than the automated detection utilities. Those are important observations because they're finding things that are missed in the original data.
Hello, my name is MacDonald and I've been part of the Globe Observer program, which is part of NASA's Citizen Science project. I've been involved in this project for the past 6 months. I decided to participate in this project so that I get the opportunity to do something cool and interesting in my free time.
Please join us because it's a very exciting thing to be involved with, to be able to report and share what I see. I'm not a scientist, I don't have a great camera, I'm not a professional, but I can be involved in something that's really important. And right now—
Hey everybody, greetings from the Arctic. Team Hearts in the Ice, saying hi.
Hi.
We want everybody at the CitSciCon to be super citizen science heroes.
It's so much fun. Join in.
All right, that was our video. Now we have a public sound check with our panel, and we'll start promptly at 2 o'clock Eastern. So I'm going to let my colleague Tara from the SciStarter team run the sound check and go down the list. Tara?
Everyone, welcome. Welcome to our attendees and those joining us from Zoom. We're just going to quickly check in with our presenters today. Let's start with Andrew. Andrew, how do you sound?
Well, let's see. How do I sound?
You sound great.
Great.
Welcome, Andrew.
Thank you.
Awesome. Elizabeth.
Hi, good afternoon.
You sound wonderful. Stinger.
Hello, how are you doing?
Doing really well. You sound great. Hi, Mark. Let's hear how you sound.
Sorry, I'm coming down the stairs.
That's all right. We'll come back to you, Mark.
Okay.
Great, but you sound good. So all of our presenters sound great today. We're going to get started in about 5 minutes. So tune in, hang on there, and tell us where you're zooming in from in the chat.
Tara, I'm going to be sharing my screen to present my slides. Should we do a check to make sure that that's enabled?
Sure. Yes, that's right. And you're the only person for this session who's doing that. I have slides queued up for Mark, Stinger, and Elizabeth.
Okay.
So when we get to your part in the main session, I'll stop sharing and then let you start. But let's do a quick test on your end.
I don't know that I have that, but let's see. Should I go ahead and try sharing my screen?
Yeah, go ahead.
And while Andrew's doing that, Darlene mentioned in the chat to chat all panelists and attendees, not just panelists. That way, all of our friends from across the globe, from Kansas City to Ethiopia, can see your comments and join in this community. Welcome. Hi, Mark. You look great.
So do you. Thank you.
Awesome. And as a reminder to our panel, when you're not speaking, you can be in the Q&A box replying to folks. I'm just showing you all a quick preview of what you're going to hear from this session. We're just going to loop this while we wait till we get to our official start time in 4 minutes. We'll be communicating with you in the Q&A box. The chat is there. You can select all panelists and attendees to communicate with everybody who's in the session on Zoom. I know we also have people tuning in on YouTube and Facebook, and this session is being recorded. So there's a whole lot of fun here. And these are the featured projects you're going to be hearing from today. How's everybody feeling so far with CitSciCon? We're on our 3rd session now.
The last one was fantastic. So was the first one, but the last one just was great.
And for those who weren't able to tune into the first 2 sessions, you're in luck. They were both recorded. You can find those recordings on scistarter.org/NASA. Hear from some amazing presenters in our first session that talked all about citizen science in schools and how you can bring citizen science to your classroom. And then our second plenary session was all about volunteer voices. And we heard from some incredible, inspiring citizen scientists volunteers, and you can check both of those out at your leisure.
I think it's cool that some of the volunteers from last session, Elizabeth MacDonald, who's one of the speakers for the session, leads Aurorasaurus. We had Donna on the last session, Donna Latch, who is an Aurorasaurus volunteer. So it's just cool that we get all these different perspectives here. And we're all collaborating together to, do real science and move science forward. We have start time in 2 minutes. I want to ask our panel if there's anything else you want to check or test or anything like that before we officially get started in 2 minutes. Any cool places people are zooming in from in the chat? Tara, do you see any interesting locations?
Any instructions for us about the Q&A? Do we answer? Do we save stuff? Do we not answer?
Please answer away. So okay. Mark, you're in the driver's seat for this one. So when we get to the Q&A section, you can ask your own questions. You can pull from the Q&A. Tara and I are monitoring Facebook and YouTube, so we'll be able to feed you some questions from there. But for the whole panel, feel free throughout, if you're not presenting, to go ahead and type some answers in the Q&A box. We want this to be an open forum for conversation.
Yeah, and we have 1 minute left, but let's just shout out. Let's see, we have folks from France, Austria, lots of folks from India, Germany, Pennsylvania, like me, Seattle. So we're coast to coast in the States, Canada. Wonderful. This is a global event. We're so happy to join you. And we're going to turn it over now to Marc.
Hey, everybody, I'm Marc Kuchner. I am Citizen Science Officer in NASA's Science Mission Directorate. And one of my jobs is to help foster citizen science around NASA and to brag about all the amazing stuff that citizen science has done. So so come with me. I'm going to share some of the achievements that we get to boast about. And they're thanks to you and to people like you who have done science with us, done amazing science with us. Next slide. Oh, okay. First, we're going to do an opening poll. Take a look at this poll and please tell us a little bit about yourself. Are you a citizen scientist, a student? I think you can choose more than one, right? Are you a parent of a citizen scientist? Maybe a museum or library staff member? Those are called informal educators. A formal educator, a teacher in a classroom, or something else that we didn't get captured in one of those categories. And I think as soon as you click on that, you get to see the answers that everybody else has put in there. I'm going to click other because I'm sort of clueless. Oh, wait, posted panelists can't vote. Okay, oh, there are the answers. Very interesting. Lots of citizen scientists on today. Very good. Thank you for sciencing with us. And we also have lots of students, and I think lots of people, because 67 and 40 add up to more than 100. I know that we have at least some people who are both students and citizen scientists. So that's really cool. Second question is up. Have you participated in citizen science? Yes or no? And have you done it for less than a year or for more than a year? Go ahead and tell us a little bit about yourself, and we'll show you the answers in a moment. No, 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 no. Well, I can't sing another bar of that song, or that could be problematic. But you get the idea. Here we go. Lots of people who have already started participating in citizen science. Hey, let me take this opportunity to say that the word citizen in citizen science, that's pay no attention to that. We don't mind if you're a citizen or not a citizen. It really doesn't matter. We welcome volunteers from any country, from all around the world. And it's that was just a word that's trying to capture the idea that we're opening up science to as broadly as possible to anyone who wants to be in it, whether you have an advanced degree in science, any degree in science, whether you remember any science from school or not. It doesn't matter. All our NASA citizen science projects all try to teach you what you need to know as you go, and they all intend to welcome new folks in. So thank you again for tuning in. Today we have wonderful presenters. We have Liz MacDonald, Andrew Westphal, Stinger Guala, and they're going to share some of the greatest hits of citizen science. They're representing some of the different divisions that we have in our science directorate in NASA. NASA does all kinds of science. Some people think that it maybe just does astronomy or just does Mars, whatever. Okay, so we do Earth science, we do heliophysics, we do astrophysics, and of course the planetary science. And our different speakers, Liz, Andrew, and Stinger, are going to share some idea of the breadth of different kinds of citizen science and science that NASA does. Next slide. NASA citizen science projects save lives. We have projects online now that study landslides, help protect millions of dollars in property and uncountable value in lives. And we have projects that are tracking the spread of disease by understanding how mosquitoes propagate around the world. Globe Mosquito Habitat Mapper is here. Next slide. This is something that completely amazes me. Just in the last few years, I've gone from bragging about how, hey, we are accomplishing some amazing stuff to we now dominate multiple scientific fields. So NASA's citizen science projects have discovered most of the known comets. I'm pausing because there's no other qualifier there. Most of the comets have been discovered by a NASA citizen scientist. All of the known samples of interstellar material, and Andrew Westphal will tell you more about that. Half of the ultra-cool brown dwarfs, that's from a project called Backyard Worlds Planet 9, that I'll brag about a little bit. Most of the long-period extrasolar planets. Most. Next slide, please. Oh, by the way, Hashima reminds me in the chat that NASA science also includes biology and physical sciences, a new division that just joined us, and that's concerned with experiments that are done in the special microgravity environment of outer space, like science on the International Space Station. Now I get to sing a song. NASA citizen scientists have discovered the first extreme T subdwarfs, Zika virus in Peruvian cemetery vases, the oldest white dwarf debris, the Dipper star phenomenon, the Peter Pan disk phenomenon, the star forming regions called yellow balls, 400,000 Martian seasonal fans, 283,000 emperor penguin nests, 8,900 mosquito breeding sites, it's up to 9 meteorites, and 1 new kind of aurora named Steve. And I invite you all to help us write the second verse. Next slide. Through this work, 191, that's now up to 194 as of last week, so NASA citizen scientists have become named co-authors on scientific papers. Next slide. Thank you, Sarah. And our papers are well cited. Here's a comparison of citation of impact, citation right, of our publications in space science compared to a couple of averages, a couple of different kinds of averages of the literature in space science. Citizen science papers from space science are better cited on average, sometimes by up to a factor of 4 than other scientific papers. Next slide. Thanks to Sten Oldenwald for that study. Well, NASA is one of the reasons that we need citizen scientists at NASA is summarized in this plot right here, which is that the amount of data that we have has become beyond incredible. It's become astronomical. So take a look at this plot. The Library of Congress has about 20 some odd petabytes of data, where each one of those is 1 million gigabytes. We have at least double that in the archives right now, and it's growing exponentially. And in the next few years, we're expecting that to expand to hundreds of petabytes of data. And for every byte that we collect from our spacecraft, we have to go ground truth that. We need people to go figure out, look at those same objects often from different directions. Like we take pictures of the clouds from above, we need pictures of the clouds from the ground to figure out what's going on. And we need people to analyze that data, go in and make sense of it, churn through it. Yes, we use computers to try to analyze it. Yeah, of course we try that. But computers, by and large, do what you tell them to do, and we need humans to do the things that we don't know to tell them to do. Next slide. So with that in mind, we are growing our citizen science program, trying to keep pace with the flow of data. We have 23 active NASA projects online. You can find them at science.nasa.gov/citizenscience, or you can go to the bottom of that scistarter.org/NASA page where you signed up for this program. And you can find our active projects are all there. And we just awarded 23 new citizen science grants in the last year. So we have 23 new teams that are working on citizen science. So I expect our portfolio of projects to expand quite a bit over the next few months. There's a lot to look forward to. Next slide. Here are a couple of the great discoveries you'll hear more about. Just this last year, the Project Sungrazer found the 4,000th comet from SOHO. Next slide. That's, once again, most of the known comets, found entire new families of comets. In Earth science, one of our cool discoveries is that folks at the penguinmap.com project, MAPPPD, used satellite images, found penguin poop all over the Danger Islands, and realized that there are more penguins on this little group of islands than on the entire rest of the Antarctic Peninsula. So that changed the name of the game for penguin conservation. Next slide. Backyard Worlds Planet 9, one of my own personal adventures into citizen science, had 4 press releases last year featuring citizen scientists as co-authors on papers. These include the first extreme T subdwarfs, 5 of the Y dwarfs. That's the brown dwarfs that pretty much resemble Jupiter. They're very much like planets, just not orbiting suns. 77 of the closest 525 known brown dwarfs, a whole bunch of interesting companions, and the oldest known white dwarf with a disk. That's a glimpse into the far future of the solar system because the sun turns into a white dwarf, and so on. Next slide. And last but not least, stay tuned for Liz to tell you all about Steve, the strong thermal emission velocity enhancement, this cool looking purple stripe discovered by Aurorasaurus citizen scientists. Next slide. And 7, Andrew is very, very modest, so he might not mention that his specks of dust are internationally famous. He might also not mention that an entire issue of the Journal of Meteoritics and Planetary Science was devoted to them. But that's the earth-shattering impact that his Stardust at Home citizen scientists have had. Next slide. And this, my last slide, is the best discovery of all, our volunteers. We've reached more than 1.5 million volunteers through our various projects, and meeting them has changed my life. And I'm really grateful. Thank you, everybody. Now to you, Liz.
Okay, sorry, I'm answering chat. Yeah, my name's Liz MacDonald. I'm from NASA Goddard, and I'm the founder of the Aurorasaurus project. Next slide. With this project, we collect not just beautiful photos of the Northern Lights for their beauty, but also for their scientific content. And so it's really great to combine those things. We're very starved of this data. Space is so large that we don't have good ways to get alerts of this, of when the aurora might be visible. And so we started the project to use smartphones and social media to do that. So now we can play a short video about the discovery of Steve.
People were out observing the aurora, and they started noticing something that was overhead as well when they were seeing the aurora far to the northern regions. It was unlike most aurora. Talked to the scientists, we didn't know what it was, and together they said, we'll keep taking observations and we'll call it Steve in the meantime. Steve is mostly a very narrow purple arc, and sometimes it has these little green features that go along with it as well that are kind of like waving fingers or a picket fence. That means that there's plasma physics happening up there to cause that light and to make these little discrete features that we don't understand yet. We now have some satellite observations from the ESA satellite called SWARM that show that Steve optically is associated with a very strong flow in the particles in the ionosphere, the upper level of our atmosphere. Steve is important for a number of reasons. It's really exciting that people armed with cameras all over the globe can capture something that we didn't fully understand and shed new light on that. It's also really exciting that this happens further to the south where there are more people, so it might be a kind of aurora that more people can see than the usual kind. We're now able to look up at the sky and see things about the aurora and this sub-auroral region that we never understood before, and then we can correlate that with our traditional observations and lead to greater understanding.
All right, thank you all. It's the end of that video. It's actually really great to share Steve with the world. It was something that was well beyond what we envisioned. We had no idea we were going to find that, and it was really great to work with the Alberta Aurora Chasers and folks across Canada as well in helping that to shed light on that. We can put in the chat some links to further discussions about what Steve is from our blog, if that's of interest. And then I wanted to share here another little video about our website that was created by one of our student volunteers and Aurorasaurus ambassadors from North Dakota, Vincent Ledvina.
Come share your memories of the Aurora and participate in some citizen science. Aurorasaurus is launching the Aurora Share campaign, inviting you to share your past experiences with the Aurora by submitting observations on our newly updated website. We are especially interested in reports from 2019. Make sure to use our hashtag AuroraShare to help spread the word on social media once you make an observation on the site. We're looking forward to sharing your beautiful reports with our followers worldwide. To make an observation on the site, you'll first want to navigate to aurorasaurus.org in your web browser. On mobile devices, make sure to use the desktop version of the website. Register an account with Aurorasaurus or log in using a Google, Facebook, or Twitter handle. This will allow you to receive alerts when the Aurora is seen near you. Of course, you can always submit an anonymous report too. If you have seen the Aurora, then click the Yes button next to the text, Did you see the Aurora? You can then make a report by filling out a short form. The information in this form gathers data like where and when the Aurora appeared and how it looked from the ground. It's okay if you don't answer all the questions. Let's run through each item together. The first box is the location. Type in the location from which you saw the Aurora event. As you type, a drop-down will appear with suggested locations. Select the location from which you saw the Aurora. You can also share when you saw the Aurora by inputting the start and stop times of the display. If the display hasn't ended yet, then you can check the ongoing box. For the Aurora Share campaign, feel free to enter a date between January 1st, 2019 and April 30th, 2020. The website will still register the observations into the citizen science database and display it on the map, but you will have to change the map's date on the main page to see backdated observations. The next set of questions ask you what colors were visible in the Aurora, and you can choose between red, green, white, pink, or if you saw something different, you can share that in the other box. Now, let us know what type of Aurora you saw. We separate types of Aurora into three main groups: discrete arcs, diffuse glow, and patchy or pulsating Aurora. Clicking the question mark icon will direct you to an article with more information about these types. Of course, Aurora takes many forms, so feel free to elaborate in the other box, for instance to mention a Steve sighting. The next information regards where the Aurora was seen in the sky. You can choose between overhead, northern horizon only, 45 degrees north or south, or the whole sky. If the Aurora changed position or didn't fit any of the options, feel free to share more. Next, let us know how active the Aurora was during your observation. We give you three options, but feel free to add your own comments. If you have any additional information about your observation, feel free to let us know. This additional comments section is also where you can give us permission to share your observation on social media. Please tell us if you prefer to remain anonymous or would like us to share a link to a web page or other information like a story with the image. Attaching an image if you have one is great, and simply clicking the select photo icon will allow you to attach an image showing what you saw. For the Aurora Share campaign, we highly encourage you to submit a photo with your report. Once you are done with everything, check the terms of use, click the Report This Observation button, and your report will show up on the map in a short time. When you and others make a real-time report, those near you with Aurorasaurus accounts will receive a notification that the Aurora has been sighted nearby. This helps them enjoy one of nature's greatest spectacles. Terms of use are important to Aurorasaurus and citizen science. In this case, we are asking you for additional permission to share your image on our social media for promotional purposes. Unless you tell us otherwise, if you allow us to share with the hashtag AuroraShare campaign, we will share your observation with your profile name for attribution. That's it. You have done citizen science. Next time you see the Aurora, kindly share it with us close to the time of the sighting when you have a chance. We will be updating our apps for ease of use next. If you have any trouble with the website or submitting a report, contact us or submit a bug report using our form, and we'll respond promptly. With your observations, Aurorasaurus is transforming the way Aurora chasers, scientists, and the interested public track, predict, and observe the Aurora. You are participating in real and impactful citizen science when you make your Aurora reports, and we thank you for being part of our efforts. The Aurora Share campaign will remember some of the most beautiful Aurora displays, and together, we can share our experiences and make new discoveries. Submit your observations on the site and make sure to use the hashtag AuroraShare if you share your experience on social media. Also, feel free to check out the other Aurorasaurus videos linked below for more info. Thank you.
All right. Yes, there's a whole YouTube of videos. You can learn more about Aurora there with us, and ways you can participate, even if you aren't in a location that might be very
local view. So we are looking down at the poles. The circles are.
Not sure what video that is. Oh, it's probably the next video on the YouTube playlist. If you can go to the next slide, there's one more slide or two more slides with one with our volunteer contributions and just a nice selection of people who have contributed. Sorry, Carolyn. I know it's a lot to juggle here. And while I'm waiting for that, I can say that the question in the chat, how far south has Steve been observed, is a really good question. I don't actually know the extreme limit right off the top of my head. It's probably, I want to say something like Idaho or Wyoming. And there were some larger storms where that was happening. But mostly since like 2016 to 2017, when we got lots of observations, there have only been small storms. So we actually need to wait for this. We need to wait for the sun to wake up in order to see more large storms and then to see how far south it can get. This slide shows a bunch of our contributors who have presented at scientific workshops, done research with advisors as undergraduates, or even high school students, contributed, like Donna Locke's amazing photo here of Comet Neowise was featured by NASA. And then you also heard about earlier Hearts in the Ice. They have collected 2 winters of very rare auroral observations from Svalbard on top of the Earth, which is really great, and we are still analyzing. And some other contributors have asked questions or created new software products to better visualize how the range of auroral activity looks and to help others. And then on the last slide here, I think my time is probably up. The last slide shows how you can get in touch with us. And thank you all very much for your interest. Mark.
Thank you, Liz. That was great.
Yes. Go ahead.
So,
Right.
Should we forge on, or can I have a quick question for Liz? I didn't hear you mention the validating tweets part of the project.
Oh, yeah, people can also participate. We scrape Twitter for tweets, and then you can upvote and downvote those tweets on the website, and they also become quality data of a real-time sighting of the aurora as well. So that's a way that people can participate no matter where they are.
Awesome. Thanks again, Liz. And next up, I think we have Andrew, right?
Indeed.
Excellent.
Right, I'm going to share my screen. And all right, can everybody see my screen? I'm going to assume so, unless somebody says otherwise. All right, I'm going to tell you about a citizen scientist project called Stardust at Home. This is the crucial and absolutely essential first step in the laboratory analyses of the very first interstellar materials ever returned to Earth. So this is what we think our solar system looked like 4.5 billion years ago. This was the time when the sun, the planets, the asteroids, the comets were forming from a cloud of interstellar gas and what astronomers call dust. Now we know, because of Stardust at Home, we know a bit more about this. And we now know that those aren't just dust. They're actually tiny little rocks. Rocks in the sense that a geologist would call a rock. That is a collection of minerals. But there's still a huge amount more to know. We know actually very little still about these particles, although we've learned a lot. And so what we're asking really fundamentally is, what are the building blocks of the solar system? What are the objects that went into making the sun, the planets, the asteroids, the comets, and ultimately made us? After all, we are Stardust. But Stardust means something else as well. So Stardust was a NASA mission. It was a NASA Discovery class mission that launched in 1999. It returned to Earth with 2 samples. It was 2 missions in 1 spacecraft. After 7 years in space, it came back in 2006. So you can see here, I hope you can see my cursor. This was the collector that Stardust used. It was a 2-sided collector. The front collected about 300 micrograms of material from the coma of a comet, Comet Wild 2. The back side, which you can see here in this picture, was exposed to the stream of interstellar dust coming into the solar system because of the motion of the solar system with respect to the local interstellar medium. It was exposed to that stream for about 200 days. And about 85% of that collector, which is about the size of a stop sign, about 1/10 of a square meter, was composed of this bizarre material called aerogel. Aerogel is a solid, but it's only a few times as dense as air. If you hold it in your hand, it's an amazing experience. It's like holding smoke, frozen smoke. And aerogel is unique in that it can capture particles going at many times the speed of a bullet intact, which is the only material that can do this. And so this was a technology that enabled us to collect this material, both from the comet and from the interstellar dust stream. But even so, this was a really hard project to take on, because we knew roughly how many particles we would get, but we knew that we would only get a few dozen in this huge area. And so this is what led us to start the Stardust at Home project. When we did the math, we realized that we would need to search about 1 million fields of view in a microscope, in a high-powered microscope, to find these tiny, tiny little particles. And we realized that that was way beyond the capability of our research group. And so we decided to recruit volunteers. And so that was a project that we started soon after the return of Stardust in 2006. And it was really the first step, crucial first step, as I said, in the analysis of these particles. So after a particle is identified by a volunteer, the very first one, which I'll show you more about in a minute, was discovered by Bruce Hudson, who was a retired carpenter in Ontario, Canada. He named this particle, which was track 30, he called it Orion. And as I said, I'll tell you more about that in a minute. But after a particle has been identified, then we extract it using techniques that we developed here at Berkeley, UC Berkeley, which is where I am. But this was done at the Johnson Space Center in the facility which curates all of the extraterrestrial samples from the Apollo moon rocks through meteorites to return samples from asteroids like Hayabusa and so on. So we extract these particles from the aerogel and then analyze them using X-ray microscopes the size of shopping malls, which could never fly in space. So this is why it's so important to have sample return missions that can bring samples back to us to analyze on the ground in our most sophisticated instruments in the laboratory. So the picture you see here in this image is the Advanced Light Source, which is at Lawrence Berkeley National Lab, but we use synchrotrons all around the world, and I'll come back to that. It turns out that the collector also had some aluminum foils, and that was a complementary collector, so we were able to identify craters in the aluminum foils. We also did an extensive campaign of laboratory experiments with hypervelocity dust guns to understand what we were seeing in the return samples from the Stardust spacecraft. And we also did a lot of numerical modeling of dust propagation in the solar system, which was really important to understanding what we saw. So the Stardust at Home project was ultimately, I think, very successful. So we engaged the help of more than 35,000 people. They named themselves dusters, and they collectively carried out more than 130 million searches of the aerogel to look for tracks, and discovered more than 200 tracks. And in fact, maybe I'll drop out just for a minute to demonstrate this virtual microscope that we used that we developed for this purpose. And let's see if I can bring this up quickly. Where is my browser? No, it's here somewhere. There it is. So this is the virtual microscope that you will see if you participate in Stardust at Home. This is just like looking through a real microscope at a sample. If you move your mouse up and down, you can focus up and down through a stack of images. So it's actually much better than looking through a real microscope, because you don't get a crick in your neck from peering through eyepieces. And there's actually a track in this image. And I don't know if you can see it, but it'll give you a second to look. I'm going to focus up and down. There's all kinds of stuff going on here. There are little particles of dust on the surface, some cracks, but you can see down here at the bottom, there is a track that is not, in this case, due to interstellar dust, but it's a track in the aerogel due to hypervelocity particle that was captured. Okay, so come back to my slides. So I guess it was in 2004 that we announced the discovery of 7 particles of what we think is interstellar origin, almost certainly interstellar origin, that were identified by the Stardust, that were collected by the Stardust spacecraft. And I just want to point out the author list on this paper. So it's 65 professional scientists, but down here, we also included in our author list 30,714 Stardust at Home volunteers. So this might be a world record for the largest author list on a paper in science. And so this is a big deal. This is the very first interstellar interstellar rocks ever analyzed in the laboratory. Now, I'm a physicist by training, and so for me, it was also very exciting that our project made the cover of our trade journal, Physics Today. So that was a lot of fun. So let me just give you very quickly the analysis of that particle Orion that I mentioned earlier. So we were able, with these giant X-ray microscopes called synchrotrons, we were able to analyze these particles, and this one in particular. So this is a particle which in its largest dimension is only 2 microns in size. And for scale, a human hair is about 200 microns in diameter. So this is 1/100th the width of a human hair in its biggest dimension. Its mass is only about 3/trillionths of a gram. What was really surprising was that it was so low density that it would float if you put it in water. But it contains crystalline olivine, spinel, and other minerals. So this really makes it a rock. And that was a big surprise. We also found that all the particles that we see are all different from each other, which is not something you would ever be able to tell from astronomical observations of interstellar dust. So this particle is still in our lab. It's in our clean room, and we're still working on analyzing it further to get as much out of it as we can, because these are so rare. Now, it's been a delight to work with the Stardust at Home volunteers, and we've gotten to know some of them quite well. Mike Capraro is one of our dusters, and he's going to be giving a talk tomorrow morning about his experiences both with Stardust at Home and with a related project called Stall Catchers, which is engaged in Alzheimer's research. I want to talk about another one. This is Augusto Ardizzone. He's one of our Stardust at Home dusters. And I want to point out the portrait up here in the upper left. This is his wife, Bianca. I'll come back to her in a minute. Augusto discovered a track just a couple of years ago. We've been going for many years now, but we're still going. And he discovered a track only a couple of years ago. Really tiny particle. It's less than a micron in size. We've analyzed it at the Advanced Light Source at Lawrence Berkeley Lab. This is a portrait of it on the left. And Augusto named this particle Bianca after his late wife. So that was very sweet. And this is something that we have offered to all of our dusters, is the opportunity both to name the particles, but also to be co-authors on any papers that come out as a result of their work. So what's next? So Stardust at Home has been going for a while. And we had a large number of people participating early on. We have a lot fewer people, and we actually regard that as something of a success, in fact, because for what, I guess 2 points. One is that our bottleneck in our process is not actually the citizen scientist activity to identify tracks. It's the analysis of the particles themselves at the synchrotrons, which are heavily overbooked. And so this is going to be something that goes on for several years. But we also are going to be accelerating our work by partnering with artificial intelligence. So it turns out that most of the fields of view that you look at as a Stardust at Home volunteer don't contain anything, because these particles are really, really rare. So it takes a lot of patience to find them. What we're going to be doing is using a machine learning approach to high grade those images that we think are most likely to contain tracks, and so that people don't have to spend a lot of time looking at fields of view or images that we're really very confident don't contain tracks. And so that will really accelerate what we're doing, and we think we'll be able to complete the complete search of the Stardust at Home collector, the Stardust Interstellar collector over the next couple of years.
One more minute.
So, all right. Well, I'm actually done. Thank you. So I want to first thank all of the Stardust at Home volunteers for all of their work. Is absolutely crucial to the success of this project, and to give the URL for for Stardust at Home. So thank you very much.
Awesome. Fantastic. And I always have so many questions for Andrew, because this is one of the projects that launched NASA Citizen Science. I think it was an inspiration to many other projects. So thanks again for speaking to us today, Andrew. And here to tell us about Earth sciences and science projects, Stinger Guala.
Hello. I'm Dr. Stinger Guala, and I'm the Citizen Science Coordinator for NASA Earth Sciences Division, and I run the Citizen Science for Earth Systems program, CSES, with Kevin Murphy. In CSES, each project is coupled to a NASA Earth observing system, and usually they generate data that helps expand the scope of that system, so it goes where the satellites can't. Maybe because of cover or something like that, or it expands the resolution. So we're getting, calibration and validation data of those systems. A lot of times they do both, and a lot of times they come up with really creative ways to have new uses for the observing systems. So I'm kind of proud of all of our PIs in here, and we're going to change things up a little bit here. I figured, why look at the past when you can see the future? And we have just now funded 8 new projects for 18 months. In fact, some of them are still getting their money, but they've been announced. And after a year, we'll reevaluate those 8 projects, and some of them will go on for 3 more years of funding. So this is your chance to see these new projects and get in on the ground floor and help them compete for the new place in the next stage of funding. So let's get to it. Next slide. This is lake observations by citizen scientists and satellites. This is our one really continuing project, and Tamlin Pavelski is greatly expanding the scope of the project to a lot more lakes and a lot tinier lakes that satellites can't see. So this is taking, where we had a pretty good satellite observation system of lake levels anyway, this is taking it to a whole new level. And you can see in the picture there. You just go out and you measure the level in the lake. There are actually a lot of moving parts to this citizen science project, but that's the main one. Next slide. So this is a project derived from an older CSS project. There are thousands and thousands of citizen scientists around the world using purple air sensors. Prakash Doraiswamy is the lead on this project, and they're working in India and California and North Carolina. And they've got some really spectacular data. So what they've done in this, what they're doing in this project, that project is still going on. You can still participate if you get a purple air sensor. But what they're doing here is they're taking the data and using some really advanced data techniques to make the data even better and combine it with some new data that's coming in now. They're seeing some really interesting stuff, and I don't want to preclude their publications, but there are correlations with COVID and all kinds of interesting stuff that's coming out. Next slide. So this is a new project, Fresh Eyes on Ice. It's based in Alaska, and they're looking at the spring breakup of river ice. And they're working very closely with indigenous peoples here. And this is a big deal because the breakup of the ice, it affects roads. It's dangerous. It affects the climate. There are a lot of environmental justice questions being answered with this, and they're just getting started. It's funny, they just kind of put up a Facebook page and got started, and all of a sudden there are all these newscasts. They're getting all kinds of press because it's the spring ice breakup. And in Alaska, that's a really big deal. So they're off to a running start. Next slide. So this is Cloud Gaze, and it's a Globe. I think most of you know what the Globe program is. It's a Globe affiliated project. So Globe has, I don't know, I think the technical amount is probably gazillions of cloud photos that they have. But they haven't been able to analyze them in the way that they'd like because they're not all tagged appropriately. And so what they're doing here is taking all of those photos and using the Zooniverse platform to tag those photos in a way that they can be better analyzed scientifically. I don't know a whole lot about clouds, but I know a whole lot about workflows. And if this works, it's going to be a paradigm for a lot of other projects. So I'm kind of excited about it. Next slide. This is water quality monitoring in the Chesapeake. And I didn't know until I saw this proposal that there are a whole bunch of areas of the Chesapeake where they just don't have water quality samples. So the CalVal for the satellites was really bad because no one had been sampling in these areas. And this project is really well aimed at getting at those issues. And it's run by one of the Smithsonian Research Centers, and they really know what they're doing. And there's a big citizen science effort already in the Chesapeake to do all kinds of things. And this is really well integrated with it. Next slide, please. This is our most ambitious project, I guess, also the longest title. It's mostly marine sampling. It's around the University of Hawaii. Nikolai Maximento is the PI, but there are dozens and dozens of collaborating organizations. And it's primarily focused on marine observations, but their real focus is on marine debris. And I think they're going to go a long way toward figuring out the plastic problem and microplastics and virtually any kind of marine debris that you can think about. Okay, next slide. This is a really focused one question CitSci project, but it involves a lot of hiking in the mountains in not so great weather, and it's going to solve one of the really vexing problems of satellite monitoring of rain and snow. The issue is satellites can see snow really well, they can see rain really well, but they have a super hard time figuring out which one is which when they're close. You know, when it's right at 32 degrees and you might get rain, you might get snow. The satellites have a super hard time with that. And this project is really laser focused on figuring out that issue. Okay, next slide. And so this is the last one. This is Fjord Phyto. So a big part of the science of this project has been running for a while. Had some early funding from NSF, but this is expanding the citizen science effort in the Antarctic, and it's a really exciting project if you like being freezing on a boat in the Antarctic. But apparently a lot of people do. They've had a lot of people signed up for this, and it's making a big difference because there's not a lot of sampling in the Antarctic for obvious reasons. And they're getting some really interesting differences in the phytoplankton flora, and they're looking at sheet flow under glaciers and things like that. So this is going to have some big impact in terms of our understanding of climate change and things like that. Next slide. And this is just some press, and the page on the left, there's our Earth Day page for CSAS, if you want to go and read more about it. I told you Fresh Eyes on Ice is already getting a lot of press just in the first couple of weeks of starting. And so you can read some news reports that mention it there. It's already in the news every day. It's really interesting. And then the Fjord Phyto project, as I said, they've been going on for a while, and they have gotten a pile of press. They have their own press page and with dozens and dozens of sites. So you can go have a look at that. So thank you. That's all I have.
Thank you, Stinger. That's fantastic. So excited about all these new projects that are coming online and joining the NASA family. Looking forward to the burst of new sciences coming out. Fantastic. So now we have an opportunity to chat, talk some more about the amazing science that's come out, and I want to see if possibly, we noticed that one of the citizen scientists who participated in the recent 4,000th comet discovery is with us, and I was wondering if we could ask him to join our little panel discussion. I didn't know that you would be online, but it'd be wonderful if maybe if Tara and
Sure. What's his name, Mark?
I don't know how to pronounce it, but it is like TR. Let's see if I can.
All right.
Like,
he's on his way to be
on
a
his
panelist.
way.
Yeah.
Okay, fantastic. Okay, so my first question should be how to pronounce your name.
Pardon me. Hello?
Yes, hi.
Hi, thank you for inviting me.
Thanks for stopping by. How do we pronounce your name?
Well, I apologize. It's called Trygve Prestgard. So I'm Norwegian, but I'm a student in France. So I'm calling from France.
Tigre, did I get that right, more or less?
Yeah, Trygve or so. Yeah, that's wonderful.
Great to meet you, and congratulations on discovering the SOHO mission's 4,000th comet.
Thank you.
I had no idea when I showed that slide that you would be in the audience. So how did you first get involved with NASA Citizen Science?
Well, I got involved when I was I was still a teenager. I was still in high school, and I always really had this passion to want to discover a comet. And I had learned about this beautiful sun grazer, this beautiful gray comet. This was back in 2011. So I don't know if you know, some of you might know Comet Lovejoy. So it was a sun grazer, and I was very curious about it, what the sun grazer was. So accidentally, I come across the sun grazer website, sun grazer project, and I learned more and more about it. And I realized this could be my opportunity to find an unknown comet. I think I really strongly partook in 2012, and it's been 9 years now. And yeah, I got help along the way. People are, yeah, it's kind of a nice community of people who enjoy helping each other. They're helping newbies and more experienced people talking between each other. There have been papers, etc. It's very interesting. It's very fun. And I have to say it's consumed a lot of my spare time.
Yeah.
Probably more than I should have.
How did you find out that yours was the 4,000th, and how did you feel?
Well, the funny thing is that I wasn't expecting to find the 4,000th. It just happened that I took my lunch break at the right time. I was working, and then I decide, generally sometimes when I have my lunch break, I decide I'll look at the Soho images quickly to see if there's something. And fortunately, I noticed this very faint comet, and I was like, oh, this is a comet, report it. And I didn't think more about it until over Facebook, one of the other comet hunters who we shared friends on, he wrote me, he said, I think you found the 4,000th. And I was like, really? So then we started counting through the discoveries, and we realized, yes, this chances are that it's the 4,000th. And eventually, the head of the project, Carl Badams, wrote me and was confirming that, yes, this was the 4,000th comet, and we will proceed to look more into this. So it was quite an exciting day.
Well, Carl's going to be upset that he wasn't here. I told him that all these sessions are recorded and they're available to watch. The recordings are available to watch at scistarter.org/NASA. So I sent him that link, and he'll probably tune in and watch this. But that's really cool. And Trygve, you ended up in a press release, right?
Yes.
Probably saw yourself name all over. Anyway, that's really cool. I hope you'll stay on for a bit. I want to ask each of our panelists the same question. I want to ask what tips you would give to citizen scientists or to your fellow citizen scientists on what you need to do in order to make a big scientific advance through your citizen science. What does it take to be the next 4,000th comet discoverer, the next Steve discoverer, the next person who discovers one of those particles? How do you get to that top level of making a major contribution? Why don't I start with Liz?
I might need a little more time to think about it, because my first inclination is to say, like we just heard from Trygve, there's a great deal of luck involved. But he was already qualified and was in position to be doing that. And so one thing we really see with citizen scientists is the expertise that people have brought from all different fields. And so that expertise combined with the project opportunity, and not being tied to what what traditional scientists have for disciplinary backgrounds, really allows people to ask unique questions that open up those discoveries. So there's luck, and then there's all of that special sauce that's really awesome.
Do you mind
to call
if
them hermetic scientists? So not scientists who are not working with citizen scientists. I like to call them hermetic scientists, as in they're kind of like hermits. Go ahead, Trygve.
My apologies. I did not mean to interrupt. I agree. There's that aspect of luck. There's always the right place, the right time, the right image at the right time. I'm personally involved in quite a few different projects, but I think more than anything, it's really the amount of time that you spend on it, because that's what's going to increase the probabilities of finding something. As a teenager, I spent hours and hours every day looking for comets, and I still spend occasionally quite a few hours a day looking for some. And I know it's the case of many different citizen scientists, and in my case, amateur astronomers who pursue citizen science project. I spend a very good amount of time to eventually find that, let's say, one golden nugget at some point, or just to be lucky to find one.
Fantastic. So luck, and you have to spend a lot of time at it.
Maybe too much time.
Too much time. Andrew, what would you add?
Well, that's a great question, Mark, and thank you for it. I think a lot of what you need to bring is exactly what professional scientists bring. I think a little bit about the Stardust at Home project. It has a heritage in a lot of things, one of which is amateur astronomy. The sky is very, very big. And because of that, amateur astronomers have contributed in really vital ways over decades to astronomy. So I think that the qualities that come to mind for me are, first of all, I'm getting a lot of echo for some reason. Maybe somebody needs to mute. Yeah, okay, thanks. An open mind. So with Stardust at Home, the first approach we thought of was to use a computer algorithm to recognize tracks. And we had some idea of what tracks of hypervelocity particles in aerogel might look like. It turned out we were wrong. So if we had trained an algorithm to recognize the tracks, we would have missed the ones that were real. It was absolutely important that humans do it because humans have a much more open mind. They're not literal minded like computers are. So I would say an open mind, a lot of patience, which has already been mentioned, a lot of enthusiasm. And it's that enthusiasm that has invigorated the amateur astronomy community for many, many years. So I guess I would say those three. Oh, I guess I'll add one more thing. Patience is important, but at least on our project, less patience will be required when we get our hybrid machine learning human approach going, because I think your chances of finding an interstellar dust particle will go way up because there are fewer people participating than when we first started, and we had tens of thousands of people participating. And also you won't have to go through nearly as many images. So less patience, but less of it.
Thanks, Andrew. So patience, luck, enthusiasm, an open mind, all great stuff. Stinger, any thoughts for us?
Yeah, for sure. So how to be successful in a citizen science project in making discoveries. What I think all of the things that the other panelists have said are absolutely true. Tenaciousness and determination are a really big deal. The people I see in especially natural history projects making a big difference are the ones who are out there every Saturday doing, sampling or surveys, or they're spending a lot of time on it. The other thing is when you do this a lot, you tend to understand the system better. So, for example, a few years ago, I was doing a study on an invasive species, and in a citizen science project called iNaturalist, which uses an AI to figure out what species the photos are. Well, AIs require training data, and what I noticed was that the more, when I did 100 specimens, the AI would get a little better. So I recruited a bunch of people, and we really focused just on a couple species. And we made that AI, by giving it really good training data, we made that AI super good at identifying these photos. And so when you form little communities within these citizen science projects, and you're all kind of obsessive about it, that's when great things really happen, I think.
Thanks so much. Thanks, Stinger. Before I hand the mic over to Tara, I just want to mention that we have, if you are looking to start your own NASA citizen science project, I'm going to put a link in the chat to a funding opportunity that is open right now. So send us your 6-page proposals through that opportunity. And thank you so much to all of our panelists, Andrew, Stinger, Liz, and Trygve, for joining at the last, at the drop of a hat. Really appreciate you all being here.
Thank you very much.
Wonderful. Thank you all. Thank you all so much. We just wanted to preview. We just wanted to preview what's coming up next at CitSciCon. Right after this session, we have Planet Palooza from 12:15 Pacific and 3:15 Eastern. Then after that, CitSci Under the Sea, featuring all kinds of fun projects related to the ocean. That's at 1:30 Pacific or 4:30 Eastern. And then finally join us for our last session of today, CitSci SIPs, at 2:45 Pacific, 5:45 Eastern. But there is an entire day of events tomorrow as well. So tune in. You can go to scistarter.org/NASA to check out all of the sessions today and tomorrow and to register. So we'll see you at the next session. Thank you all again.